Exponential growth or decay function. Here's the formula and definition. Let y sub 0 be the amount or number present at time t is equal to 0. Then, under certain conditions, the amount present at any time t is modeled by y is equal to y sub 0 e power of kt, where k is a constant. Y sub 0 here is the initial amount, and y here is the future amount. Now, when you see exponential growth, k here is positive. When you say exponential decay, k here is negative. So again, this is the formula here. Y is equal to y sub 0 e power of kt. Example. So you're given a table here, and given the table, the first column is your year, the second column is carbon dioxide in ppm. So I can assign here 353 as y sub 0, and I can also say 2000 is my y here. And looking at the time, the difference between this 2275 minus 1990, that would be my time here. So I will say 2275 minus 1990. That would be my t. And that is equal to 285. So my formula is y is equal to y sub 0 e power of kt. So I have my y already there as written. That's 2000. And my y sub 0 is 353. My t is 285. Then I can look for my k now, which is the missing item here. Okay, so here's the first question. Find an exponential function that gives the amount of carbon dioxide y in year x. And that's the formula that we're talking about. And our y, it's 2000. Our y sub 0 is 353. That's the initial amount in ppm. And then e power of k, our t is 285. So that's our equation. Okay. We can actually change, if you want to change the t here in terms of x, because you have y and x here. So we can rewrite the equation into y equals y sub 0 e power of kx, which is our t. So it's just the same thing. We're just replacing the variable. And then from here, we can find our K. Okay, so by taking ln on both sides, but first we can actually eliminate 353 on the right side by dividing 353 on both sides of the equation. So 353 here and 353 here. So this 353 is gone now. And then we take ln on both sides. So we'll have ln. The purpose of taking ln on both sides here, so we can bring down our variable k. So that would be ln e 285k. Using the power rule or the power property, I can bring down the variable k. So the next step would be ln 2000 divided by 353, and we will get 285k here, ln e. So ln e is 1, then we can solve for k here. So by dividing 285 on both sides. So k can be solved. So k here is equal to, so the strategy here is do not calculate 2000 divided by 353 yet. So we need to have an exact answer and do not round off your answer. So now you can calculate. You can say ln 2000, enter this in your calculator, divided by 353. Don't forget the grouping symbol, then divided by 285. And then our answer is k is equal to 0.006. So that would be our k. And if you want to round that to the nearest 4 decimal places to the right, so that would be 0.0061. So let's just have 4 decimal places, and that's our k there. So now we can have the equation, which is the model equation. I'll put it in a different color. So you're going to say now y equals 353 e. Our k is a positive, so this means this is exponential growth. Exponential decay would be, k would be a negative. Okay, and t, we change that into x. So this would be the model equation. Model equation. And we can use this equation to answer other questions, okay, for the problem. So we're just having letter A here. So for letter B, it says estimate the year when future levels of carbon dioxide will be double the pre-industrial level of 280 ppm. Okay, so our model equation a while ago, it's y equals 353, and we have our k here, so e power of 0.0061 x, so that would be the time. Okay, now it says here double what? The 280 here. So when you're going to use this equation, it says double. The future amount is y, so double, you just multiply that by 2. So 2 times 280 would be your y. So that would be 2 times 280 because of the word double. That would be our y, 353 e power of 0.0061 x. So it says estimate the year. So you're looking at x here. So x is the time, and this is our unknown. Again, it says estimate the year when future levels of carbon dioxide will be double the pre-industrial level of 280 ppm. Okay, so on the left side, 2 times 280, by calculation, that would be 560. And then our goal here is to find the time, the year, so solving for x here. So I will divide this by 353 on the right side to eliminate the 353 and do the same thing on the other side. So this one cancels out. So this is similar to what we did on letter A. We're taking ln on both sides to bring down our x using the power rule or the power property of logs. Ln is natural log. So we have ln here also. That will be e 0.0061x. And then we have to apply the power rule. So the power rule, it gives us here ln 560 divided by 353, and that would be 0.0061 x. On the other side, since ln e, we can bring down this power here to the side, and ln e actually is 1, so that cancels out. So that would be our answer there. And we have to eliminate the 0.0061 by dividing the same number and do the same thing on the other side. Okay, and this cancels out, so you will have x on the right side, and we calculate the left side to get the answer. So that would be ln. Press your ln button in our calculator, and that's 560 divided by 353 divided by 0.0061, and the answer would be 76. So that would be 76 years. So we're not going to round that. We will just show that 75.65 in decimal. That could be round off to 76 years. And that's our answer for letter B. So If you're going to look back to our table a while ago, we have 75.65 here. We add this to 1990. So 1990 is the initial year. We add this 75.65, and we will get 2065. 0.7. So it says estimate the year. So we have 75.65. We add that to the initial year, which is 1990. So we will get 2065.7. So at that year, the pre-industrial level of 280 will be doubled. So our answer here is on that year, 2065. So we're not rounding that up because 2066. So it's not the beginning when the pre-industrial level will be doubled. So it's beginning at the middle of 2065. So that's year 2065 is the correct answer for letter B here. Okay, next example. Suppose 600 grams of radioactive substance are present initially, and 3 years later, only 300 grams remain. So observe that the number of grams is getting smaller. So we will have the decay here. So remember the previous example, it's getting bigger, double. So it means that's growing. Here it's decaying. So it means it's 50% reduced. So determine the exponential equation that models this decay. So we'll still use the same equation. Y is equal to y sub 0 e power of kt. And then our y is here. This is our y. Y sub 0, I mean. And the future, since this one is getting smaller, is your y, which is 300 at this point. Let me see. Okay, so that's the right one. So we'll have 300 for y, and remember that our 3 here is our time. So y sub 0 is 600. Then e, k, the t is 3. So we can find our k now. So we can write the exponential equation model for this decay. So we divide this by 600 and divide this by 600 here. So this cancels out. And we're taking ln on both sides to bring down our k using the power rule. So we'll get ln e 3k here. K times 3 is 3k. And then we can place this 3k to the side using the power rule. So ln e is actually 1, that cancels out. So our answer is ln 300 over 600 equals 3K. And then we divide 3 on both sides. So dividing 3 here and dividing 3 here to eliminate the actually 3. So K is equal to ln 300 divided by 600 divided by 3. Okay, and then we will calculate that in decimal form. So ln 300 divided by 600 divided by 3. It gives us a negative value. So K here is a negative since it's decaying. If it's growing, then that would be a positive value. So this one is a negative 0.231, and that would be our K. So the exponential equation model would be y is equal to 600 e power of negative 0.231 t. Okay, you can have that model equation, or you can replace t with x. A while ago, it was specified that the t would be our x. Okay, and that's similar to this thing also. You can replace your t with the variable x. Okay, so you have that model equation. Okay, last problem. How much of the substance will be present after 6 years? So let's write the model equation again. So that's the model equation. So our t here is 6. So we're just plug that in. So it says how much substance will be present after 6 years. So we're looking for y here. So that would be 600 e power of negative 0.231. Our t is 6. That's a number of years. And then we'll just calculate. And that would be our y, which is the future amount. Okay, so that would be 600 times your E. Okay, power of, it's a negative 0.231 times, don't forget to put this in a grouping symbol, parentheses, because you have two terms in the exponent. Okay, and hit enter. Then our y value is 150. So that would be the answer. Okay, for letter B. Okay, so the unit here, because we're talking about how much of the substance will be present, the unit here is in grams. So we can put the unit grams here. So 150 grams would be the future amount.